Imagine this for a second. You've got two villages. In the first one, folks just dig down 10 feet and boom, a reliable source of water. But just a few miles down the road in the second village, they have to drill a massive 250-foot borehole just to see a single drop. So what's the deal? Why such a wild difference? Well, the SSC JE exam absolutely loves testing you on the science behind this exact mystery. Welcome to this explainer. Today we're building from scratch to total exam-level mastery. Consider this your ultimate conceptual shortcut for the SSC JE. If you stick with me, you're going to be able to solve practically every groundwater question the exam can throw your way.
Here's our quick roadmap for today. First, we'll solve that groundwater mystery. Then, we'll look at zones in the water table, break down aquifers, untangle porosity and permeability, understand wells, and finally lock it all in with an SSC JE rapid revision. Let's get right into it.
Section 1. The groundwater mystery. Let's solve this by tracing the actual, physical journey of a single raindrop, starting right up at the surface.
When rain falls, it basically has three possible fates. Number one, it can just evaporate right back into the air. Number two, it can become runoff, rushing over the surface into our rivers and lakes. But number three, and this is exactly where our focus needs to be, is that it can seep directly into the soil. We call this process infiltration. As this infiltration goes deeper and deeper, the water starts filling the microscopic pores in the soil. And that critical step, that is exactly what creates the groundwater we care so much about as civil engineers.
Moving on to Section 2, Zones and the Water Table. So what actually happens is that infiltrated water travels deep underground.
To build a really solid mental map here, picture two major layers right beneath your feet. First up is the zone of aeration. As water travels down, the soil pores in this layer contain a mix of both air and water, so it's completely unsaturated. But eventually, that water hits a point where it pools into what we call the zone of saturation. Down here, every single pore is completely stuffed with water, zero air. This right here is your actual usable groundwater storage.
Now, the boundaries separating these two zones, it is incredibly important. The water table is defined as the exact boundaries serving as the upper surface of the zone of saturation. So here's the crucial takeaway. When a question asks for the definition of the water table, you immediately look for the phrase upper surface of the saturated zone. It's an absolute recurring favorite on the SSCJ. Seriously, lock this one into your memory.
Section 3. Aquifers, where water lives. Now, what's truly fascinating is that water doesn't just pool equally everywhere beneath the water table. The actual type of rock or soil matters immensely.
Because not every rock can store water, we have a very specific term for the ones that actually do. An aquifer is a geological formation, think rock or soil, that can effectively do two things. It must store water and it must transmit water. That dual requirement is the catch. If it just holds water like a sponge but won't let it flow, it's virtually useless to us. It absolutely has to both store and yield that water to earn the title of an aquifer.
So, we can classify these aquifers into a taxonomy of four essential types. We've got the unconfined aquifer, the confined aquifer, the perched aquifer, and the Artesian aquifer. Let's break down exactly how each one of these functions. An unconfined aquifer has an open top. It recharges directly from the rainfall dropping right above it. Easy enough, right? A confined aquifer, on the other hand, is trapped like a sandwich between two impermeable layers of rock or clay, which means the water inside is actually under pressure. Then we have the perched aquifer. Think of this as a temporary pocket of groundwater sitting on a very localized, small, impermeable layer way above the main water table. I want to explicitly shout out the perched aquifer right now, guys. It is a massive previous year question or PYQ favorite. Finally, the Artesian aquifer. This is a special type of confined aquifer where the water pressure is so intense that if you drill into it, the water rushes to the surface completely on its own.
Section 4. Porosity, Permeability, and Flow. Let's shift gears from where water lives to the actual rules of how it moves. We really need to clear up a massive conceptual confusion that trips up thousands of students.
You have to realize that porosity and permeability are not the same thing. Getting these two twisted is a super quick way to lose easy marks. Porosity simply measures how much empty space, or voids, are available in a material. It dictates the maximum storage capacity. Permeability, however, measures how easily water can actually flow through that interconnected space. Simply put, it's storage capacity versus flowability.
This classic comparison brilliantly illustrates the difference. Look at clay versus gravel. Surprisingly, clay actually has a very high porosity. It can hold a massive amount of water.
But because its microscopic pores just aren't well connected, its permeability is shockingly low. The water gets stuck. Gravel, on the other hand, might have lower porosity than clay, but its permeability is extremely high, so water just rushes right through. Examiners absolutely love this trick, so remember, clay holds water, but it flat out refuses to share it.
So, since water does flow, we need a mathematical rule to describe it. Enter Darcy's law. You can basically think of this as the Newton's law of groundwater. The formula is Q equals K times I times A. Q is the discharge. K is the coefficient of permeability, which is usually measured in meters per second. The I is the hydraulic gradient, essentially the slope that's pushing the water along, and A is the cross-sectional area. But hey, what's the absolute most important thing to remember here? This formula is valid only for laminar flow.
Section 5. Understanding wells. Okay, so we know how water moves underground, but practically speaking, how do we actually get it back to the surface so we can use it?
Now, while there are plenty of open wells and tube wells out there, I want to focus entirely on the single most heavily tested well type on the exam, the Artesian well. When you drive a well into a highly pressurized, confined aquifer, you're tapping into immense natural pressure. And because of that intense pressure, the water just shoots straight up the pipe on its own. The defining characteristic you absolutely must remember for the exam is that an Artesian well requires absolutely zero mechanical pumping.
Section 6. SSC JE Rapid Revision. We've built a fantastic mental map today. Now, it's time to put that map to the ultimate test with some actual SSC JE previous year questions.
Question 1. What is the definition of the water table? Take a brief mental second. Got it? It's the upper surface of the saturated zone.
Question 2. What properties does clay generally possess? Come on, we just drilled this one. Clay has amazingly high porosity, but shockingly low permeability.
Question 3. Under what specific condition is Darcy's law valid? Let's rapidly knock this one out of the park. It only works under laminar flow conditions.
And question 4. Does an artesian well require a mechanical pump to bring water to the surface? Think about the immense pressure of that confined aquifer we talked about. The answer is a resounding no. No pump required.
To wrap things up, here is your 60-second rapid-fire summary cheat sheet to lock everything into your visual memory. Ready? Rainwater seepage is infiltration. The upper unsaturated area is the zone of aeration. The lower fully saturated area is the zone of saturation. A water storing and transmitting formation is an aquifer. The primary flow equation is Darcy's law. And finally, the classic example of high porosity but low permeability is our good friend, clay.
If you've truly internalized these concepts today, you are beautifully positioned to solve the vast majority of groundwater questions on the SSC JE. I promise. We'll be diving deep into soil, water, and seepage in our next explainer. But before we go, I want you to consider this. If artesian wells flow naturally without pumps, what actually happens to the Earth's surface when we extract that pressurized water faster than nature can replace it? Think about that, review these concepts, and remember, deeply understanding the core material is literally your ultimate shortcut. Catch you in the next explainer.